final speaker of the day before we have the final discussion is Britta Westner, who has come quite recently to Aarhus University from Constance. She's a postdoc at the Center for Integrated Neuroscience, working with Sarang. She ended back on all sorts of sophisticated MEG analysis of what the retina might actually be up to. But in parallel with this kind of, in itself, really interesting work, Britta is also one of the people here at the university who pushes forward the ideas of what would it mean to actually create open programs and open data and open software in terms of sharing how you can understand and analyze the data. So, Britta, take us away.
Thank you for the introduction. I'm happy to be here. I'm going to be talking about open software in a very broad manner today. First of all, I have to do the old programmer's joke and say, hello world. A bit about me. As you just heard, I'm a neuroscientist here at Aarhus University. I'm mostly interested into the visual system. I record MEG data. And I also have some side projects on machine learning and source reconstruction. But probably more important for today is that I'm contributing to open source. I'm contributing to the M&E package, a package for MEG and EEG analysis and visualization. And there I'm mostly contributing to the beamforming module, some kind of source reconstruction for EEG and MEG data. I came to this just as a background during a Google Summer of Code project I did. So Google Summer of Code is that thing basically where Google funds students for 3 months to contribute to open source. And that's how I got started in that whole open source universe. So today, I hope that together we can find some answers to the following questions, namely, why is open source essential for open science? What are best practices for open tools? And that's spanning from your own code to open source software. How does all this facilitate reproducibility? And as a last part, I would like to talk about the question whether there is an open source crisis or not. We talk so much about crises on this workshop, so I thought I had to contribute too. Okay, let's jump right in and answer the question, what is open source? Well, software or code is considered open source if that code is freely available, if it may be modified by anyone who wants to modify it, and if it may be redistributed by anyone who wants to do so, of course, citing the original source. So one of the most prominent open source things out there is actually an operating system. It's Linux. But open source is not limited to operating system. You have programming languages out there that are open source, for example, R or Python. You have toolboxes. For example, the machine learning toolbox scikit-learn. You have what I just introduced to you, M&E Python, or kind of as a corner case, Fieldtrip. Fieldtrip is another toolbox for EEG and MEG analysis. Fieldtrip itself is completely open source, but it relies on MATLAB, which is not open but closed source. So we have kind of these corner cases as well. And then we have foundations. Google, of course, is not open source, but they do have open source things like Android or their big machine learning library, TensorFlow. So you can see it's like a big universe out there that is open source, and all different kinds of people and organizations can contribute to that. So why do we talk about open source here? Why does science or open science need open source? Well, I'd like to quote Richard Feynman, the physicist, who also was an advocate of good science. And he said, "What I cannot create, I do not understand." So if you're not able to recreate an analysis of someone else, you might ultimately not be able to understand it. And to quote Fernando Perez, who also is a physicist, but most known for inventing the interactive Python, IPython, he said, black boxes do not belong in science. And this means, like, from doing your analysis to actually plotting, there shouldn't be any black boxes in there. And what you describe in a paper might not be enough to get rid of those black boxes. So I would just want to back up a bit and consider what is needed for reproducibility. Well, we need to consider the computational tools. That's the scripts you've been using. That's the toolboxes you've been calling. That's the programming language you've been using. And believe it or not, it's the operating system you're on. Because, for example, if you just consider regression, right? Regression relies in most toolboxes on something called open BLAS. And that is like the basic linear algebra subprograms that are called. And those are dependent on which operational system you're on. So if you use Linux, you might get different answers than if you use a Mac or Windows. This is not a big point, but just to raise awareness that this matters if we talk about reproducing results. Of course, you need to consider the data. Without the data, it will be hard to reproduce anything. We need to consider that you share your work, and you need to communicate your work. So for the computational tools, the answer is use open tools and share your own code. Share your data. Then sharing of your work, and this includes, for example, your analysis scripts, that should be done in an easily accessible manner. So it needs to be out there and retrievable for others without having to email you first or going onto that web page that no one can find. So it's also the question of how easy is it. And then in the end, you're going to communicate your work on whatever channels you do it. Some do it by publishing. Some like to tweet it. And then also include the links to your code and your data. OK, so how do I actually make a data analysis reproducible? Looks familiar? Well, reproducibility starts with you. So if you cannot reproduce your results at a later stage because 2 months later you don't know if it was data analysis in capitals or data analysis final 2 that was the last version of your script, it's going to be hard for anyone else to reproduce if you can't do it yourself. So I would like to advocate for using version control. Then also you need to document your code, because if you don't know what you did in line X 2 months later, how would anyone else know what you intended to do? Let's look a bit deeper in that, a word about version control. So version control is awesome because it is basically your very own time machine. The principle is easy. You're responsible for setting timestamps, and the file only exists in the most recent version. But you get a log of changes over time, and that makes it possible for you to also go back in time. My recommendation to use is Git. It will get clear a bit later why I recommend Git, and this is how it could look like. This is one of my projects. So if I now find out that, yeah, that typo here, that kind of changed the whole analysis, and I want to have like that stage back where this typo was still in the script because this typo is really important, I can just cancel everything I did after that. I might also find out, oh, when I did those big modifications, I'd like to keep everything I did before that step, and I'd like to keep everything after that step, but that step has to be gone. That's possible. So all those different file names are not needed anymore, because you have the perfect timeline of whenever you'd have a timestamp, and you can go back to any of those time points easily and look at that script as if you would get into this little TARDIS here and travel back to that. So now we kind of solved reproducibility for your own sake. How do I make my code public to make anyone else, to give anyone else the possibility to reproduce my results as well? And I think the first question you might have is, where? Where do I put my code? Do I put it on my own homepage? Well, you could do that, but there is also systems for that. And those systems are, for example, GitHub, or GitLab, or Gitbucket. And as the names kind of give away, they integrate perfectly with your own Git version control system. So they're basically just an online extension for that. And then the second question is, how do I share my code? And there is actually kind of an etiquette for sharing code. And I would like to emphasize this, because maybe a lot of us have been there, where we found this awesome paper with this awesome analysis, where we thought, wow, I want to learn how to do this. And then you see they have their code online. That's even better. I can actually try it out myself. And you look at the code, and you spend 2 days, and you still don't know what's going on. There are rules. So the first thing is include a license, because without a license, nobody is allowed to use your code. The second thing, and this is an important one, is format your code. And because it's such an important one, I'll get to that in just a slide. Basically, things like coding styles or line width really matter, although they might seem a little bit over the top at first. Then, of course, document your code. Put comments in there, put doc strings in there, give a project description at the top level of your folder to make people understand what you actually did. And also important, note down dependencies and versions of other toolboxes you've used, because things change. Bugs in toolboxes get discovered, other things change, and at the end, everyone does the same as you did, but they get different results just because one of your dependencies changed. OK, I'd like to demonstrate to you why coding style makes things easier. Consider this code. I hope you agree that it's kind of hard to, I mean, of course, most of you might not be familiar with those functions because they are from the MEG world, but still, what's going on here? Also, the lines go on and on and on here. I cut them off because I didn't have enough space. There are linters for that. A linter is basically a little test program that runs in the background and tells you what's wrong with that code. And as you can see with all that orange here going on, oopsie, now that's interesting. Huh. Turns out you can mute your presentation if you ever need it. It's the lower right button. You can see there is a lot wrong with this code. So let's try to improve it. Let's first let's resolve every one of those warnings. Then it looks like this. Looks better, right? Now every function call has their own line. And you can see all of the code because it's cut off or taken into a new line after 80 characters. You could actually even view this code now on your mobile phone if you wanted to. You can see how many objects are produced by this code easily now. But we can do better. So now I just added a bit of lines, and it just gives the code some space to breathe, right? Now the important one. Now we know what's happening here. I apply a filter, and I pre-allocate a matrix. I resolve a generator. And if you're really, really good, I call a lot of things in those functions here. And if you want to be good to other people, but mostly to yourself, because you might want to reuse that in 4 years, write a little description of what you actually feed in here. So this is just things that in the beginning seem overwhelming, and you think like, I just want to get my analysis done, right? I don't care if it looks nice or not. But if you start doing this, it will come very natural to you, and it will save you a lot of time in the future, but also other people who might be interested in using your functions or reproducing your analyses. So I promised you to get back to GitHub. And I would like to make a case why GitHub facilitates open science. And here's a big disclaimer. GitHub itself is not open source. GitLab and Gitbucket are. So that's something you might want to consider. A personal note, I'm still on GitHub. The reason for that is a lot of the big toolboxes started out on GitHub because GitLab and Gitbucket, who are open source, were not around back then. And while I can fork a project from GitLab to GitHub or GitHub to Gitbucket to work there on my own, it's basically impossible to work together with other people. So I get a lot of comments about that actually. Why are you on GitHub? That's not open source. Well, that's the reason, just because I want to contribute to toolboxes and I want to have everything in one space. But just as a disclaimer for you, if you are new for signing up, GitHub is not open source. It's owned by Microsoft now. Anyway, so why does this facilitate open science, or maybe is even like a model for open science? On those platforms, you can share your code, but you can also follow researchers and toolboxes to stay up to date. So it's basically kind of like Facebook for nerds. You can collaborate on projects, either with just like your 2 favorite collaborators, or you can collaborate with people all around the world to build a toolbox that you make open source. You can fork projects. That means you just take that project and make it your own and continue from there. Nobody, like this is built into the GitHub system, and I think this really is open science, right? And last but not forgotten, you can contribute to projects, for example, open source toolboxes. So the next thing that is needed for that whole pipeline to work out is, of course, the data. I know that there, at least in Denmark, is a lot of debate at the moment whether it's legal and in which way it's legal to share your data. I want to bracket that off today, also because we are very international here, and just make a case for why we should aspire to share data within the legal constrictions that we have. So I would like to look at one possibility for sharing your data online, and that's the open science framework. So here, just one example. The great thing is, especially if you publish a paper about those data, is you get a DOI with your repository online that you can take. A lot of journals nowadays want that from you. But let's look a bit closer. So you can have like a wiki for your project on there, where you can have a description, a link to the paper, and all of this. But what kind of gave it away for me is you have your data storage down here, where you could have all your subjects, but you have a direct integration of GitHub. That means on Open Science Framework, you can share your data and code together, but you still have all the freedoms that GitHub gives you in updating your code. So if I now go to my GitHub repository and find a typo and update that, it will be reflected here. So that's like a nifty thing that makes it easier to keep those things together, but not have like 5 repositories of your code online. Okay, so what I would also like to emphasize is that I think there are 2 different kinds of reproducibility out there. There's the technical one. That's, yeah, I have my code online and I have the data online and I also have a link somewhere in the paper, but that's about it. And the other one is the one we should aspire to, and that's the practical reproducibility. And that has a lot to do with how easy it is to actually rerun your analysis. And that's the difference, whether it takes you 2 weeks to reproduce the results of XYZ et al., or just 2 hours. And here I would like to kind of introduce you to a tool called notebooks. They are especially great for smaller data sets or just the visualization if you have a lot of data or a lot of loops in your code. So those notebooks, in that case, I picked the Jupyter notebook that runs R for you, it runs Python for you, it runs Julia for you. There's also the R Markdown for those who are closer to the R universe. And those are great tools because they not only have your code, you can write descriptions, as here. You can have figures. So if we consider this example, I took that from the LIGO Open Science Center. That's the notebook where they show you how they found evidence for gravitational waves. So you can see they have a bit of info here. So that's the data quick view of the LIGO Open Science Center. It's a version from 2016. And if we would scroll down a bit, we would see that you have cells with code here. And if those code, for example, outputs a figure, you have the figure together with the code. So you have your whole analysis, you have the figures embedded there, and you also have the freedom to put whatever descriptions you would like in an easily readable manner. So I think they are really great tools, but I kind of still need to get the data somewhere, right? I need to download it, and then I need to put it in a folder, and the notebook in the same folder, so the notebook sees the data, and I might need to get some path set right, so that notebook sees the data, and all of this. I also still need to create the right environment, because I might have different Python versions, or different software that is used, or the operating system might be different, and I still cannot reproduce their results. And since a couple of years, there is an awesome thing around that solves all that, and that is Binder. So what Binder does is, and actually what I just showed you before was not a pure notebook, but a notebook in Binder. Here you can see how it's loaded. It's the same LOSC tutorial. What Binder does, it takes all of those problems into a cloud. So if I were to publish such a notebook as a researcher, I would give my data, I would set the versions of the operating system, of Python and all this, and it would be reproduced online for you. So if you click that link, it says loading repository, and what it does is it sets up a Linux operating system, it sets up the Python version that was used, it sets up the software in version XYZ, then it loads the data for you, and you get to see this notebook, and it's completely live. You can change those variables, and the plot will change as well. And I can look into some of your heads, and you're thinking, wait, couldn't we write papers like that I've been there. Like, I've seen that paper and I thought, wow, why didn't they include the standard deviation here? That would be great information. You could do that. You could just write the little line, plot standard deviation, and it would update for you right there. And it's out there. Practical reproducibility, like in its finest right now. As one example, eLife. eLife now has papers, here one about tumor cells, that work like the binder examples I just showed you. So if you were to open this document, it tells you it's a reproducible document. And if you click on a little button next to the figure, you get the code. And if you change the code, the figure changes as well. So they have kind of the same principle. They have the data online, they have the environments online, they have the code online, and you can just sit there and mess around with it and see what it changes. So up till now, we mostly looked at your code, your data analysis, but there's also all those toolboxes out there that you use for your data analysis. And I would like to advocate at this point for contributing to them. So the question is, why should anyone contribute to open source? Well, it turns out over half of the GitHub contributors do that to solve a problem. They contribute once because they have a solution for a particular problem or bug they found in a toolbox, and they want to contribute that solution back to the toolbox and the community. Some do it for reputation. It's something you can put on your CV, I assume. We'll get to that a bit later again. And some do it for the community. As Brett Cannon said, one of the Python Foundation people, I came for the language, but I stayed for the community. So if you're intrigued now, you might question, well, how do I do that? How do I get started, right? Well, maybe you have the case that you are using toolbox XYZ and you know that something is just not working right. And you're a bit annoyed by that. And there's a solution for it. Open an issue on GitHub. So just to show you, so you really don't have an excuse how it looks. This is the GitHub page of M&E Python. You would just go and click that button, new issue, and then they actually walk you through it. They tell you what you have to describe. And you can see, like, here are some of the most recent issues we have. And then you get the awareness of contributors, of the maintainers, of the core developers of that toolbox, because it's their daily job to look at this list, and they will tell you, well, we're gonna look at that. Or do you want to look at it? Another case might be, you know that there's this bug or this thing that is not working right, or maybe also that thing that is not there at all, and you know how to fix it. Well, go ahead and open a pull request. So a pull request, basically, you already give them the code as you think it works the best for them. So here is a list of pull requests from the same repository, and if we just look at the first one, you can see, like, there's a description of this pull request, what it will do. And then, just to also show you what it would look like on the code, you would change stuff in the code, and then with that instance of the code, open the pull request. And the nice thing about GitHub, which also would work like that for your own code if you collaborate with other people in your lab, is you have, like, in red the line that like it was before, and in green what you propose should happen instead. And then you take it from there and you enter a stage that is called social coding. So other people will give their comments on your code. They will tell you what maybe to do a little bit different. They might ask you to do more or to drop some lines. All of that is then basically a process where you get guided through. So if you do want to get started, most communities out there, most toolboxes have a how to contribute wiki page that you should read with some nifty little details, what you should know beforehand. And most importantly, most communities are very welcoming. So if you signal that you're a first-time contributor, they will walk you through it. They will help you with all the questions you might have. So don't think, well, but I'm not really. No, if you want to do that, and if you have an idea of what can be changed, just appear online and signal them. I'm here, I'm eager to do that, but I don't really know how, and they're gonna take it from there with you. Okay, so that's the part about open source in science, and I hope that I convinced you that open source is essential for open science, because the analysis step cannot really be a black box in the whole framework of your study. I showed you that this really spans from sharing your own code to having open source toolboxes and either using them or also contributing to them. I hope that I made a case for practical reproducibility, that this is important and that it's not just about dumping it somewhere online, but thinking about how this is done best for the science community. And I hope that, at least in some of you, I sparked a bit of interest for contributing to open source toolboxes if you don't do it already. So now I would like to switch gears a bit and pose the question whether there's an open source crisis. And I want to start with an example that is not really science, but illustrates the problems we might be having. So let's look at OpenSSL. That's a toolkit for internet connection security. And in 2014, it's been used by 2/3 of internet traffic worldwide. It got known in 2014 because there was a bug discovered in their code, and it's known as Heartbleed. You might have heard of it. And that kind of made a lot of people look at this toolbox and find out in surprise that this toolbox, an open source toolbox, was only maintained by a handful of volunteers. So 2/3 of the internet traffic was secured by a handful of volunteers. Another example that is closer to science is the Python ecosystem. NumPy, as one of the core toolboxes in the scientific Python ecosystem, only secured stable funding in 2017. Before that, some of the contributors had some funding for a few years, but never was the toolbox as such contributed. And Fernando Perez, who we met on one of our first slides, the inventor of IPython, estimated in 2011 that the scientific Python world relied on approximately 30 people. And I hope that you see what a big problem for science this is. We rely in science, but also a lot of companies, just to also say that, on, if we use Python, 30 people. So let's look a bit closer at that. 2/3 of the top projects on GitHub are maintained by only 1 or 2 people. They have more contributors, but the core knowledge about those toolboxes is concentrated in just 1 or 2 people. So if you would take an analogy with a company and you would ask, if I find the most important people in that company and rank them, how many of those people do I have to fire until this company basically is not able to operate anymore? That in software is called the truck factor. It asks what minimum number of developers have to be hit by a truck before a project is lost. And Avellino et al. Looked at that for some of the most important or biggest projects on GitHub. And they kind of get frightening results. I talked about the version control system Git. Git is open source, Git is on GitHub, and Git has a truck factor of 12. So if the 12th wrong or right, from which angle you look, people get hit by a truck, this project is lost and there is no more Git because the knowledge about how to maintain Git is gone. Scikit-learn, the machine learning toolbox that is used by, for example, Spotify, but also a great deal in science. A lot of AI research relies on scikit-learn, has a truck factor of 7. IPython, the interactive Python that is used by everyone who uses Python, has a truck factor of 4. And pandas, which is used for data frames, also used a lot in science, has a truck factor of 2. So apart from that, or maybe also like playing into that, are other factors. One of them is funding. And kind of also related to that are the needs of maintainers. And I think a big problem is that those needs are traditionally not considered. If we look at a quote by the GNU license guy, Richard Stallman from 2005, he says, "Our goal should be to spread freedom and then defend it. That is more important than making our software popular, which would just be catering to our own egos." So basically what he's saying is there is no place for egos in open source. It's about the user, not the maintainer. But that kind of has the problem that if the needs of maintainers are not met, if they are overworked, if they quit and there's no one else to step up for them, then we will lose open source projects. And related to that is the problem of burning out on projects. For example, due to workload, due to not having funding, due to not looking at the needs of the maintainers, and especially nowadays due to toxic feedback. This is a blog post by James Kyle. James Kyle is a developer and maintainer who did a lot for a toolbox that was used for JavaScript integrations. And they changed a major feature in their toolbox. And people got really, really angry. And he says, the angry response has been overwhelming. Every single day, I'm reading someone else rant about how awful of a job we are doing. It's been hard to stay motivated. And just as a side note, he's not paid for any of that. But we are in science, so I would like to, at the end of my talk, have a spotlight on academia and how academia, from my perspective, contributes to this open source crisis. Let us listen once more to Fernando Perez, the IPython founder. He says, software work in science can be career suicide. Let's look a bit closer and look at Chris Holdgraf. He is a developer for Binder, which I just showed you, and also Jupyter Notebooks. And he says, something I didn't expect when working on Binder and Jupyter. Not being attached to a specific scientific field is really scary. You realize how much the academic world doesn't understand how to value work that isn't attached to publications in your domain. So, to just bring the problems up here on this presentation, the incentive structure of modern academia does not fit with developers at all. Because if you develop code, even if you are just a contributor that contributes once a year, if you contribute once a year and you take the time to write the code and be reviewed and review other people's code, in that time you put that contribution to open source over writing a paper and getting it published. And you can see how this scales, right? Like if you get to become a maintainer of a toolbox, you have a lot of work for this toolbox, and this prevents you from publishing. So I summed it up as contributions instead of publications. That will show on your CV. So what I said earlier about you have a reputation, you can put it on your CV, well, maybe we are not there yet. We are not there yet. And this also falls together with an interesting trade-off, because we're in science, so a lot of the toolboxes not only require you to be able to program, they also require that you have a very distinct knowledge about problems. Let's say it's statistics, or it's source reconstruction, or it's whatever field you're working in. And then you have the trade-off between having the expertise to actually tackle problems and having the time to do so. As a PhD student, you might have the time to spend a month contributing to a project, but maybe you might run into limitations in your expertise, and then as a senior scientist, the other way around. So I tried to come up with some solutions here to end on a more positive note. And personally, I think we need to reach a critical mass. If enough people share their code, because that also needs time. You need to prepare your code to go online. You need to actually put it online and all this. And if enough people start contributing to open source, that might change the view of the whole scientific field about whether this is just a pet peeve of some people or something that is essential to our academic culture. And I just want to remind you again of the truck factors you have seen of some projects. I think we are also at a point where users outgrow contributors by so many factors that we need to reconsider where we put our money. Because if scientific Python is gone, well, maybe we can switch to R or the other way around, but I hope that I could show you that it's kind of important that we think about this as well and don't take it for granted that the toolbox you're using will still be around in a year. If you're teaching or supervising, you might want to consider open source. Not only using it, but also advocating for it, raising awareness about where those toolboxes come from. And if you are in the position to hire, you might want to consider open source sacrifices as a good thing, and not only look at the publication list of a person and say, oh wow, this person only published 5 papers, the other one has 10, overlooking that the first person spent a lot of time into trying to keep that scientific open source ecosystem alive. If you're writing grants, maybe you would like to put that into your grant, that this is something you would like to do, or that you would like a student to do, to also let funders know that this is something we should care about. So again, can't emphasize it enough. I hope that I showed you that open source is essential for open science. I mapped out some ways to higher reproducibility. I hope I showed you some ways to contributing to open science and maybe also gained some or sparked some interest in you. And I hope that I raised awareness of the open source dilemmas we have and maybe also gave you some ideas to cope. And I would like to end with acknowledging some people. I first would like to acknowledge my supervisor, Sarang, who is just sitting over there and not only contributes to open source himself, but always encouraged me to do so. I would like to thank Google Summer of Code, because I think it's an awesome program to get young scientists or non-scientists into open source, and it's also the way I started. And I would like to thank the people of M&E Python for guiding me along the way, and you for your attention. Thank you.